Next, we will discuss on how we can do the DC analysis for the bias circuit. So our objective of this DC analysis is to get or to obtain the Q point, to obtain the value of collector current ICQ and VCEQ, the collector emitter voltage. So how this is the general procedure for DC analysis. So first of all, so if you see the amplifier circuit with the capacitor, because when you want to do the DC analysis, the first step is to replace the capacitor with open circuit, because in a DC operation, the capacitor has very high impedance, so it can be replaced by the open circuit. Okay, and then when it is replaced by the open circuit, you may find that some part is not connected to the amplifier, so you can remove the source and the load from this one. So we'll only have this amplifier circuit only. Okay, next, the second step is write the KVL along the base emitter current path. So we have here, this is the NPN. So in this course, we will only focus on the NPN BJT. So this is NPN, this is collector, this is base, and this is emitter. So the first KVL is KVL along base emitter current path. So we have this current path, or we can call it the input loop. So this is the input loop. Okay. So when we do the KVL at the base emitter current path, so we need to consider the voltage drop across the base emitter terminal. So because the base emitter is a PN junction, okay, base emitter is PN junction. So and then we consider the BJT is at the active region. So this is the important concept that need to be understood is when we design the BJT for the amplifier circuit, we need to assume that the BJT in active region. The BJT is active region. So the condition for the active region is the base emitter junction in forward bias. Okay, base emitter junction is forward bias. So that's why, so VBE will always assume VBE is equal 0.7 volt. Okay, so this is depend on the value of the barrier potential. If you assume the barrier potential between base emitter junction is 0.65, so VBE will be equal 0.65. But for this case, we will mainly use the VBE is equal 0.7 volt. Okay, so this is the first thing that you need to consider when you do the KVL. And then the second one is when you do the KVL, because you'll have IB terminal. You have the current at the base IB and also the current at the emitter. Okay, so in your KVL, you might have the IB term and IE term. Okay. So you can relate the IB and IE with this equation. IE is equal to beta plus 1 IB. Okay, this is the equation. So where this equation come from? So we have discussed in previous class the relationship, the current relationship. So we know we have the beta here. Beta is the current gain of the BJT. So beta is IC over IB. So beta is IC over IB. So IC for NPN is pointing downward. So this is IC over IB. So beta is the DC gain. So beta is DC gain. So output current over input current. So IC over IB. And then we also have the relationship between these three currents. This is IE equal to IB plus IC. So from these two equations, so we can get this one is IB and then IC is equal to beta IB. So that's why you get 1 plus beta IB. So this is the derivation of this equation. Okay. Okay. For simplification, you can just memorize this equation. IE is equal to beta plus 1 IB. Okay. So next, you can solve this IBQ from the KVL, and then once you have the value for the IBQ, you can get the ICQ from the by using the beta. Okay, now you have solved the IC. So the third step is you need to write the KVL along the collector emitter current path, or we call it output loop. So this is the output loop, and then in the output loop you will have the parameter of VCE, the voltage across collector with respect to emitter. So now you can solve the VCEQ. Okay, let's go to the example of fixed bias. So this is a fixed bias circuit. So there is no resistor at the emitter. So we have collector resistor and we have the base resistor. And then at the input we don't have any source. So but we have this capacitor C1 and we have this capacitor C2. Okay, the bias DC voltage is plus 12 volt. So we can go through the step, the general procedure one by one. Okay, first the capacitor need to be replaced by open circuit. So we remove this capacitor. So C1 and C2 are removed. And then the second one, KVL at the base emitter. So we'll do the KVL at the base emitter. So which is one is base, this is base, this is emitter, and this is collector. So we will do the KVL along the base emitter. So along this base emitter. So where is the current? The current flow should be from the DC voltage, and then it will go passing the base emitter junction until the ground. So this is our so-called base emitter current path or input loop. Okay, we'll do the KVL at the input loop. KVL PE is negative 12 plus a voltage drop at the RB. So the current is IB. Okay, so the current is IB times RB is 240 K, and then so we go this base emitter. Along the base emitter we have 0.7 volt, so this is plus 0.7, and then we come to the ground. Okay, now we see the KVL here. Okay, VBE. Okay, now we done here. VBE is 0.7, and then since we don't have any voltage drop at the emitter, so no need to apply this one. So this is not applicable. So now you can solve this IB. So the IB is equal to 12 minus 0.7 over 240. Okay, so this is equal to, okay, let me calculate this one. So 12 minus 0.7, then divide by 240. So this is 0.047 milliampere. So you get the IB. So when you get the IB, you can calculate the ICQ or IC. IC is equal to beta. So how much the beta? Beta will be given. Usually will be given. So beta is 50. So beta IB. So 50 times 0.047 milli. So this is equal to 2.35 milliampere. So you got the IC. Okay, so this is done. And then the second part is for the Q point, you need to calculate the VCE. So the VCE from the KVL of collector emitter. So VBL's collector emitter is from the VCC. Okay, and then will pass the collector emitter until the ground. So this is the output loop. Okay, so the equation KVL is minus 12, and then plus the current at the RC is IC. So IC we have 2.35. So we have this one is 2.35 milli times RC is 2.2. And then here VCE is unknown, so this is plus VCE is equal to 0. So you can get the VCE is equal to 12 minus this value. So 2.35 times 2.2 is equal to 5.17. So this is 12 minus 5.17, 6.86 volt. Okay, this is the answer. So we have the IC is 2.35 and VCE is 6.86 volt. Okay, this is the Q point. And then if you recall back what we have learned in the previous week on the load line. So load line we have, this is IC versus VCE, and we have here, okay, ideally in this load line we want the Q point at the center of the load line. So in other words, okay, this point is called the cutoff, equal to VCC, so 12 volt. So ideally we want the Q point at the center, so means that it should be half of the VCC. Okay, so the half of 12 volt is 6. So you see here the VC is 6.886. So this is around, it's not much different. So means that this bias circuit is okay. So this is the design of bias circuit is okay. Okay, so next, what if we need to calculate these values? Okay, first of all, what is VB, VE, and VC, and VBC? Okay, so you can draw this one. So this is collector, this is emitter, and this is the base. So you know the VCE is 6.86 6.86 volt. And then you also know that the VBE is 0.7 volt. Okay. So the question is how much is VB, VE, VC and VBC. Okay. So let's do the VBC first. So VBC is the base with respect to the collector. The base with respect to the collector. This is a VBC. Okay. You need to take note that VBC and VCB is not the same, because VBC is VB minus VC, while the VCB is VC minus VB. So these two parameters, VBC and VCB, should have a similar magnitude, but the polarity is different. Okay, so we go back to the question. What is VBC? So VBC is actually a VBE minus VEC. Okay, VEC. So you get this one, VBE is 0.7 and VEC is minus VCE. So this is 0.7 plus VCE is 6.86. So this is 7.56 volt. So this is the answer for VBC. Okay, how about VB, VE and VC? So for the VB, you need to see the whole circuit. Okay, see the whole circuit. We can redraw this one. So we have, this is RC, and we have E is connected to the ground, and then we have, this is RB, and then this is 12 volt. This is 12 volt. Okay, so what is VB? Okay, VB is from here you can see the VB, because since this E is ground, so you know that the VBE is equal to VB minus VE. So VE is ground, so VE is equal to 0. So VE is equal to 0 because the emitter, this is VE, is grounded. So VBE is equal to VB minus VE. So VBE is 0.7, VB and VE is 0. So VB is 0.7. Okay, you know we have calculated VB and VE. Okay, and then you see this one, the VCE is 6.86 volt. So VCE is equal to VC minus VE. So VE is ground, VCE is 6.86 equal to VC minus 0. So VC is equal to 6.86 volt. Okay. Okay, this is the answer for this question. So the thing that you need to be able to do is, you need to able to differentiate between the voltage at the point or the voltage across two points. Okay, for example, VB here is the voltage at the base point, but VBC is the voltage between base with respect to the C, collector. Here, and VCE is the voltage from the collector point with respect to emitter point. So VCE.